The Tan-Chord theorem that everyone has been waiting for has finally arrived. So how do we prove this theorem? Like always, I like to go through the converse of this theorem, and after that I explain what that converse is saying. The converse of this theorem states that two tangents drawn to a circle from the same point outside the circle are equal in length. It says these two tangents here, as long as they are from the same point and they touch this circle once, therefore this length here is equal to this length here. What I mean is that AB is equal to AC. As long as those tangents are from the same point outside the circle, they are equal in length. So how do we prove this theorem? Like I always do, I draw my constructions, and after that I unpause the video to explain what I did. So I will see you after the pause. Yeah, here I've drawn these lines here. In my construction I said draw OB, which is OB, draw OC, which I drawn here, and I joined OA. And hey, did we even read the statement, or we just jumped to the proof? Because when I kind of see these questions, I skip the instructions, the information there. It says in the diagram below, we always know O is the center, but not always. So don't do that. AB and AC are tangents. AB and AC are tangents to the circle. Prove that AB is equals to AC if these two are tangents to this circle from the same point. And we are required to prove that AC is equals to AB. So in our proof, we are required to prove AB is equals to AC. In our proof, we will say in triangles OBA, OOBA, and triangle OCOCA, we can take out main relationships. We can say angle in OA, we can say OBA, angle B is equals to angle C is equals to 90 degrees. Of course, there must be a reason. Reason is that what is the reason? Radii bisect tangent. This should be your reason. Radii bisect tangent. And then what other relationship can we give? We can see that OA is common in both. So we can say OA is equals to OA. Reason is that OA is equals to OA. The reason is that this is common. This is a common side, and then we should have said OA is equals to OC. OB is equals to OC first, but yeah, OB is equals to OC. The reason is that they are the radii. Actually, this should come first, followed by this, and I wrote it the other way around, but I think you will fix it. And then let's move on. We can conclude that OBA, triangle OBA, is congruent to triangle OCA. The reason is that we have a right angle, we have this hypotenuse side, and we have another side, or can say 90 degrees hypotenuse side. So either say 90 degrees HS or RHS is the same thing. So we have a right angle, a 90 degree angle in both triangles. We have equal radii in both triangles. Therefore these two lengths are equal. Therefore AC is equals to AB, or AB is equals to AC. Doesn't matter how you put it, but yeah, we proved this theorem. But we are not done, because this theorem come in two ways. It may come in this way, or it may come this way. So yeah, you might you might what, Mar. Sometimes I'm just speaking. Some people, they might think I'm crazy, but yeah, I kind of forget what I want to say at some instances. But yeah, let's read here. In the diagram below, O is the center of the circle, AC is a tangent, and chord AB subtends APB. You can see that here. And then prove that angle A is equals to angle P. You have to prove that this angle here is equals to this inner angle here. Or you can also prove that this is equals to this. But here we are required to prove that this is equals to this here. So how do we do this? Of course, there must be construction in every proof. So I'm gonna make construction. Of course, you're not gonna notice this process. So I'm gonna pause and draw some few lines and then explain what I did. So I'll see you in the next few seconds. And my construction is I drew this diameter here. The diameter passes through the center, and I joined DP here as a draw diameter AOD, which is this here, and join DP, which is this here. And I said this is P1, P2, this is A1, A2. But we know that angle A, this whole angle here is 90 degrees, and this whole angle here is also 90 degrees. And you will know why in a second. Yeah, required to prove. Required to prove what? That angle A1, what's angle A1? Angle A is equals to APB here. Don't mind this A1 here, because I think it's kind of a mistake here. But we are required to prove that angle A as a whole is equals to angle P as a whole. So in our proof, right, we will say proof, and then what do we do now? What do we do? Yeah, we will say angle P1 plus angle P2 is equals to 90 degrees. And yeah, you can see that I'm trying to remember how to prove this here. Like, you don't have to cram the whole steps of proving, because sometimes they might bring W, X, Y, Z, and you are used to cram those prove that A is equals to P, but in the test they might bring W, X, Y, Z, and you might be confused. So don't try to cram these things. Try to prove them on your own, and when you're struggling, you can come back to this video and see how to prove it without creaming, you know, because yeah, creaming kills, you know. Yeah, it kills. And someone might ask, who did it kill? Who did it kill? But yeah, I don't know. I just heard, you know, people were saying, if you cream, you'll die. Yeah, and where were we? Proof. What did I say? Angles is an angle in semicircle. Semicircle. And angles in a semicircle, like I said, did I even say it? Because sometimes I'll say, like I said, only to turn out that I didn't say anything. But yeah, and 180 degrees according to angle at center theorem, it says this angle here, angle at the center, which is 180 degrees, is half angle, is twice angle at the circumference. If this is 180 degrees, this is half of this angle here, which is 90. That's why all the time angle in the semicircle, they will always make a 90-degree angle. And what can we say? We can say that A1 plus A2, remember these are angles, is equals to 90 degrees as well. The reason is that diameter bisect tangent. Bisect tangent. Tangent. Ooh. Diameter bisect tangent. And then what can we say also? We can say that, like I told you in the previous video, this shape here is always gonna come, no matter what. It's always gonna come, this shape of angles in the same segment. And we said that this angle here, oh, you cannot see, this angle here is equals to this angle here, and this angle here is equals to this angle here. You can see A1 is equals to angle P2, this side here, angle P2, because of what? They are angles in same segment. These angles here, they are angles in the same segment. That's why they are equal. If A1 is equals to P2, A1 is equals to P2, let me isolate this first. Let me put this as P1 is equals to 90 minus P2. And then similarly, we can say A2 is equals to 90 degrees minus angle A1. I just made A2 and P1 the subjects of these formulas. If A1 is equals to P2, if they are the same, then obviously A1 is equals to, P1 is equals to P2. Is equals to P2. This is just the the rule of thumb, and I think we have proved this theorem. And yeah, I'm gonna see you in the next videos, so take care, and I will see you in the next video. And yeah, this is it.